Welcome to this lecture in which we will explain how to convert our system to the controller canonical form. AB is generally not in controller canonical form. Can we convert our general system to this form? What happens to control law? Let us recall the material already covered in the previous video. Here is the closed loop expression. This is the control design problem, and we assumed A and B to be in controller canonical form, and we got the control law to be the last row of alpha C of A, where alpha C is the desired polynomial. But as mentioned earlier, AB is generally not in controller canonical form. We can show that there exists a non-singular constant matrix M such that the transformation M inverse AM equals A bar, M inverse B equals B bar, such that A bar B bar are in controller canonical form. That is, even though A and B may not be in controller canonical form, we can transform them to A bar B bar, which would be in the desired form. And this is possible if and only if, which we will often abbreviate as IFF, the matrix C, script C, defined as here B, AB all the way up to AN minus 1B, where N is the dimension of A, is non-singular. That is, we can do this transformation to the desired form if this script C is non-singular. If so, A comma B is said to be controllable. We will see the implication of this in a subsequent video. Assume for now that we have such a matrix M. In a subsequent video, we will demonstrate that such a matrix indeed exists. So let us define a new vector x bar as follows. Let us write x as M into x bar, and recall that M is non-singular and constant. So we will start with this in the next slide. So we refer to this as the coordinate transformation. We let the original vector x as the matrix M into x bar. So this equation, state space equation, becomes, in the place of x you put mx bar, in the place of x once again you put x bar, here x bar of k, here it is x bar of k plus 1 plus bu of k. So we are not changing u is same as before. Let me bring this m to the right hand side, so I get this expression on the right hand side. Let us define new variables, A bar as M inverse AM, B bar as M inverse B, and as I mentioned earlier, u is not changed. So in the transformed coordinates, that is in the new coordinates, we get in the place of M inverse AM as A bar, M inverse B becomes B bar. By construction, we have got A bar B bar in controller canonical form. Of course, this will become clear when we discuss how to obtain this M. We will postpone this to a later video. For the time being, let us assume this, that we have indeed got A bar and B bar in the required form. So we have transformed coordinate state space expression. Everything has this bar except this u, as I mentioned earlier. The new state x bar is defined by x equals mx bar using this coordinate transformation matrix M. This is how we define A bar and B bar, and A, B and A bar B bar are in controller canonical form. Because these are in controller canonical form, I can use Ackermann's formula. Okay, and then we ask the next question, can I get this k bar directly in terms of m and k, so that k is already available and can be implemented directly. Remember, if we have the control law only in terms of transformed coordinates k bar, then what we have to do is we have to do lot of work, but k is in the original coordinate, control law in the original coordinate, this is what we want. Okay. To answer that, let us recall the control law, minus k bar x bar, k plus v of k. Why do we do this? Because we want to use the transformed coordinate. In the transformed coordinate we get this directly. In the transformed coordinate we can get the control law by observation. That is the reason why we want it in the form of k bar. So let me write the expression for x bar. So x bar is as given here, m inverse into x, which is what I write, m inverse into x, and this k bar I write it as it is, plus v of k, and this is nothing but k in the original coordinates, and hence I get the expression k equals k bar m inverse. So if I were to discuss this problem without any transformation, I would have written as uk equals minus k into x of k. So as a result, that k equals this k bar m inverse. So let me go back and substitute all this, x bar of k plus 1 equals this expression, and let me substitute for u of k, which is minus k bar x bar of k, and then v of k. So I have simply substituted this expression into this, and I have grouped the term. I have not made use of this expression, but I am going to do this in the next slide when we start talking about the closed loop expression. The characteristic polynomial will be unchanged by transformation, which is what we would want to demonstrate in this. Let us recall the expression for phi, which is this polynomial, and because we are working with transformed coordinates, we will put a bar everywhere. Let us substitute for these transformed coordinates. A bar equals m inverse am, b bar equals m inverse b, and k equals k bar m inverse. This is what we derived in the previous slide. So let me substitute here. In the place of I put m inverse m, in the place of a bar I put m inverse am, in the place of b bar I put m inverse b, in the place of k bar I put k post multiplied by m. So I have got this, and I have m inverse at the beginning in every one of these entries, and m as the last entry in every one of these entries. So let me pull these out, m inverse from the left and m from the right. So I get this expression, m inverse on the left hand side, m on the right hand side. So I get identity multiplied by z here, and then a comes here, and then bk comes from here, and we have the determinant of products. This is nothing but product of determinants. So when I do that, I group m inverse and m together, and this is nothing but identity, and determinant of an identity is 1. So I get this equals phi of z, nothing but, so I get phi of z, which is nothing but this expression. We have seen this expression before, phi of z equals determinant zi minus a minus bk. So we see that the characteristic polynomial of the original and the transformed systems are the same, and the controller in the transformed coordinates is given by this using these bars. So let us now try to get this k bar, or in fact let us try to get this k in terms of the original coordinates, untransformed coordinates, so that we can implement that controller directly. We need to evaluate this polynomial alpha c evaluated at a bar, so it has powers of a bar. So let us evaluate powers of a bar below. So a bar squared is nothing but, on substitution from here, m inverse am into m inverse am, these two cancel each other, we get m inverse a squared m. What about a bar cubed? Once again we have to do the same thing, a bar squared we write from here times a bar, and it becomes m inverse a cube m. We can continue this and we get, for all powers we get m inverse that power and m. Similarly we can calculate a bar b, which is m inverse ab. We can calculate all of these are straightforward. We can calculate a bar n minus 1 into b bar also. Now let us calculate our script C matrix. Remember we had b, a, b and so on. Let us write this in terms of the transformed coordinates, and let me write for b bar as m inverse b and pull out this m inverse here, and then a bar b m inverse ab. So I pull out this m inverse, so I get ab here and so on. All of these have m inverse coming in the front, so I pull out, I get b ab a n minus 1 b, which is nothing but the script C matrix without the bar. So I write this as m inverse script C without bar. So from this we can see C bar is non-singular if and only if script C is non-singular. Remember when we introduced the concept of this transformation matrix M, we said that is possible if and only if this script C matrix is non-singular. So now we see that if and only if this script C is non-singular, we have this script C bar is non-singular because these two are related by this non-singular matrix M. So we will start with this expression in the next slide. We are still trying to get the direct controller expression, which we will complete in the next slide. So C bar equals m inverse into C. So C is invertible if and only if C bar is invertible. So as I mentioned in the previous slide, I want to get k bar in terms of original coordinates, and recall the expressions for a bar squared, a bar to the power n and so on. All of them have m inverse in the front and m at the rear. Let us substitute these in the polynomial alpha c. So alpha c of a bar, which has powers of a bar, will have m inverse in the front, m at the back as given here. So let us calculate k now directly. K equals k bar into m inverse, which also we derived in a previous slide. So let us substitute for k bar here. What is this? This is nothing but the Ackermann's formula when a bar and b bar are in controller canonical form. I have written this for k bar only. I have to write this m inverse also, which I write now, and substitute for this alpha c of bar from here, m inverse alpha c of a into m I have written it here, and of course this M inverse comes from here. Now I can simplify these two. So I have simplified, I write down the remaining things, and what is M inverse? So let me write it from here as here. So M inverse is nothing but C bar into C inverse, which I have written here. Now I have written this in blue because I am going to simplify this product. What is this product? This is nothing but the last row of C bar, which is nothing but En transpose. I have not shown it here, but I would want you to evaluate this. Remember, A bar and B bar are in controller canonical form. When those are in controller canonical form, evaluate this matrix C bar and evaluate the last row, you will find that is nothing but En transpose. I have not shown this, but it is easy for you to verify this. So I get this expression for K in terms of this script C. So this is the utility of the Ackermann's formula, that we can get an explicit formula also for the general case. To conclude, in general AB is generally not in controller canonical form, but we can bring it into the desired form when controllable, that is when script C is invertible. For this general case, we derived Ackermann's formula in this video. This is the last row of a slightly different matrix, which was pre-multiplied by En transpose as we discussed in the previous slide. This brings us to the end of this presentation. Thanks for joining. Goodbye.